Okay, good afternoon. I am Supriya, host for the session. Welcome to 146th episode of Creative Online Weekend Talk. Creative is a group of people who are eager to gain new knowledge. Creative tagline Knowledge Square, sharing of knowledge increases our knowledge. Vision of Creative is to build constructive thinking on various domains. And every weekend we organize online weekend talk and we live stream our program on our YouTube channel Creative GBD. Today we are excited to discuss an incredible discovery, the oldest radio lobes found trapped inside a cluster of galaxy. In this episode, we will learn how scientists found these ancient radio lobes, the technology they used, and what this means for our knowledge of the universe. We will hear from expertise and explore the fascinating detail of this breakthrough. For today's session, we have Dr. Sujit Paul sir with us today, and I welcome one and all for today's session, and I call Divya, creative volunteer, to introduce today's speaker. Over to you, Divya.
Thank you, ma'am. Good afternoon, one and all present here. I'm Divya, volunteer of Creative. I'm here to introduce our today's speaker, Dr. Sujit Paul, who completed his master's degree in physics at Pune University before moving to Würzburg University in Germany, where he obtained his PhD under the DFG German Research Foundation International Graduate School Program in 2010. He then returned to India as a postdoctoral fellow at the Inter-University Center for Astronomy and Astrophysics in Pune. In 2012, he received the SCRB Young Scientist Fellowship, and in 2013, he was awarded the DST Inspire Faculty Award by the Government of India, joining the Pune University Physics faculty. Recently, in June 2023, he transitioned to the Manipal Center of Natural Sciences, MAHE, as an associate professor. Dr. Paul has an impressive record of high impact publications in top international journals, including Science. He is a regular reviewer for prestigious journals such as Nature Astronomy and Nature Communications. His distinguished career includes international fellowships and guest professor positions like the SFB Fellowship for DESW Hamburg, Germany, and the Excellent Cluster Origins Guest Professor Fellowship, Munich, Germany. He has served as a guest professor at Hamburg Observatory and a guest scientist at the University of Munich, LMU. Additionally, he is actively involved in various committees and professional bodies, including the National Supercomputing Missions, NSM, the Square Kilometer Array India Consortium, SKAIC, and the International Astronomical Union. This is all about our today's speaker, and I'm welcoming you, sir, for this session, and I'm welcoming all the participants of Reactive and volunteer of Reactive to this session. Thank you, ma'am. Over to
Thank
you.
you. Thank you, Divya. Over to you, sir. Sujit, sir, you are muted.
Can you hear me?
Yes, sir. Yes, sir. Go ahead.
Okay. Yeah, thank you, Supriya and Deepa, for nice introduction and giving me this opportunity to speak in this forum about my research. So, welcome everyone who is in the online session, listening to my talk, and have a good day. So today I will be discussing about recent discovery. It's a couple of years back we discovered the oldest radio lobes that were found in a galaxy cluster. I will come to all the jargons. I mean, you can you know that scientists work with jargons which is specific to their field, and that may not be understood by the general people. So what I will do, I will begin with some very basics of the astronomy so that you get accustomed with the terms, and then we'll proceed with the results that I want to show today. So my the minute it's working. Okay, fine. So this talk will be outlined like this. Initially, I start with the something basics of astronomy. Then I will go to the discovery, and I will show the analyze how we analyze it and what the results we obtained and why it is important, and then a little bit about the concluding remarks. So let's start with a very known thing which we every day see, that is our sun, that is our nearest star. I mean, it is since we see it every day, so we know much better about this. And I'm starting with this thing because this is the most nearest astronomical body that we see, and then there will be scales and mass scales, everything that we determine depending on the our nearest star. So I mean, many of us know that this is the medium size or standard size star in our whole sky, and it is nearest one, and having mass in our known scale, it is 10 to the power 30 kilogram, and size is about 1.4 million kilometer. Size means the diameter of it. So this is the scale that we will be working with, and this is the smallest scale that we'll be working with actually, because the things that we'll be discussing, that will be quite million, trillion times bigger than this. But if we take it in kg or kilometer, all those things, that will be so high in number that it won't be very easy to handle. That's why we will take some scale which is I mean, which gives a, because larger thing, so we need larger unit also, so that we do not get lost in huge numbers. So anyway, this is sun. But if you see where the sun is placed in our even in our own galaxy means, you know, that this is called the Milky Way, which even we can see on our sky. I mean, see means nowadays because of the city lights we cannot see it very well, but if you go a little bit out countryside, you can see some very bright almost across the sky one narrow patch can be seen, which is nothing but our galaxy. Because we are within the galaxy, we see it on our sky, spanning the whole sky in our night sky. So if you see here, you will see that our solar system is somewhere here in some arm. I caution you that this image is not real image. It's a artistic impression, because we cannot see our galaxy on the plane of the sky, because we are already on the galaxy itself. So we see the cutting cross section of the galaxy actually. But this is from our various studies, we came to know that our galaxy must be looking like this. And there, if you see the red point, that is our solar system. That is not even our earth or sun. This is the whole solar system in this scale. It's a roughly scale, but this is how. So how big our galaxy, you can imagine from there. and that is also, this is the observable part of our galaxy. That is optical galaxy. If you see it in different other wavelength, lower energy wavelength, then you will see it is much bigger than this. Anyway, the size of this is like around 10 to the power 5 light year. Now we came to something called light year. Light year means in 1 year, how much the light travels. Our galaxy itself is 10 to the power 5 light year. That means if we travel with the velocity of light, then also to cross our whole galaxy, it will take 10 to the power 5 year to cross with light velocity. You can understand how big it is. And the mass is trillion solar mass. Now in the scale of solar mass, you see solar mass was 10 to the 13 kilogram. Now we are talking about trillions of solar mass. This is the kind of mass that our galaxy has. And this is not the end. Just a minute, you will see that how actually you look towards our galaxy itself. So this is our galaxy on the sky. With a very sensitive telescope, it has been observed. But even with our this eye, we can see when we go in the countryside, and we can see this whole patch of bright sky. That is the galaxy. It is originally how we see our galaxy. So this galaxy, our galaxy is one of millions, trillions of galaxies that we have in our universe. Our galaxy is kind of this middle one. This is spiral one. There can be various other kind of galaxy like elliptical. These are major divisions. So that can have elliptical size, which is the biggest one. Usually biggest galaxies are elliptical. Spirals are medium kind of, and some irregular galaxies are also there. And these are the real examples below. Now, here we come to more bigger picture. So this is a part of our universe. It is not the whole universe. It is a very tiny part of our universe. And in this sky, you can see that each point here, each black point is actually one galaxy. Now we can understand how big it is. So one galaxy is here. Within that galaxy, our solar system is a tiny one, and within that tiny solar system, we are most tiniest one planet. So you can understand that how big our universe is, that only a small patch itself is I mean trillion times bigger than our own solar system. So this is something called redshift. I am not going into discussing on redshift. This is something you can consider that on in the line of sight. If we look in the line of sight, how deep and what are the structure is there. So this is the line of sight. If we look into the sky, through the sky, the structure will come like this. And if we see it on the sky, it will look like this. Now you can see that galaxies are not really placed randomly. You can see some pattern, right? Some kind of patterns are there. Some void region, some very dark region. So these dark, dense region are called galaxy clusters. Okay, so today in our discussion, actually we'll be discussing about both the galaxy cluster as well as galaxies sitting inside the cluster. Okay, so I think I at least gave you the idea how the structure in the universe are arranged. So they are not really random. You can see the structures, and this is, let's say, one big galaxy cluster sitting here. So some filamentary structures are there. They are connecting, something like that, and that's how the galaxies are placed in the sky. So let's go into something else, that how we detect these objects. So this is something which we see in through our optical telescope. I will come to various kind of telescope, but before that, optical telescope, possibly all of us know it, right? Like from our childhood, whatever telescope we have seen, it is optical telescope only with some mirror or sometimes with the lens. So if you see our sky, you will see some bright part is here, right? And some smaller part and something which has this kind of extension, these are the stars. These are very near to us. This is maybe from our galaxy which are seen, but behind that you can see these are the galaxy itself. So as we go deep in the sky, the bigger object will be seen as smaller one, and that can be seen as points and all this stuff. So these each point are actually galaxies, except these things. There may be some galaxy clusters as well, because that is too far, and size wise, because it is too far, size wise with some nearer galaxy, it will be almost looking similar. But we can distinguish, scientists actually can distinguish depending on various characteristics. In the center, there is a galaxy sitting, the bright galaxy is sitting. So now let's think about that. What is the radiation that we are actually observing through optical telescope? This is nothing but if I don't know who I mean the people that who are listening to this talk have some idea about the physics little bit. If you have little bit physics idea, then you can understand that every atom or molecule, they have a characteristic spectra which comes from the you know that electron and protons are there. So protons and neutrons are in the center, and electrons moves around this nucleus, which is made up of proton and neutron. Those electrons may get excited, and then when comes down to its ground state, it emits, which is called the spectra, electronic spectra. So what in optical regime we see is actually nothing but the electron spectra. And another thing is that these are very hot objects, so we see black body radiation. I am not going into the details of black body radiation, many of you have heard about this. So these two kind of radiation that we can see in the optical through the optical telescope. Next, going to the same object, same galaxy. Now I am looking with a different telescope, which is called radio telescope. So if you see, radio has the lower energy than the optical region. So this lower energy, actually it propels much of electrons and emits in radio waves. But you see that when the same object, we are looking through two different telescopes, we see them completely different. So with optical, this is what we see. With radio, you see it is such a big object and having this kind of structure, which is called jet structure. I will come to that point because we will discuss more on the radio galaxies. But how this emission happens? So this is nothing but electrons, because we know that universe is full of magnetic field. So when high energetic electrons move around this magnetic field, it actually emits some emission, which is called synchrotron emission, and this emission come in the energy range of radio waves. Radio waves is actually electromagnetic waves, not the radio that we listen to. So that is sound wave, but this is electromagnetic wave. Why we call radio? Because there is a I mean that all the communication that happens without wire, that is done by radio waves. And since our this radio means radio station also use that wavelength, that is also called radio. It's not really radio. What we listen on the radio is sound wave, but the transmission that happens is through radio waves. Nevertheless, now the same object in another wavelength. You see, this is in X-ray. Okay, So you see this magenta color halo kind of thing, which is again much bigger than the optical size of the same galaxy. And this happens because of the X-ray emission. X-ray means X-ray that we know is actually the medical X-ray is some emission that is created in the lab. But this X-ray is not created in the lab. It is some emission that happens in the astrophysical body. How it happens? So you need some heavy nucleus, and near to that, if electron passes through, it bends because of the interaction, electromagnetic interaction, and it bends. And when it bends, actually it gets accelerated or deaccelerated, which emits some emission, because deacceleration means loss of energy, and that energy goes out. And this is, since it is a kind of breaking the path, or whatever you can call it, that is called Bremsstrahlung in German, and that gives you the X-ray emission. Fine. So this is what we understood from the whatever the observable, and how this observable emission is taking place in the sky. So these are the major three kind of wavelength that we observe. So if you see our sky, actually electromagnetic wave is actually distributed in huge range. So I'm talking about in wavelength. If I talk about in wavelength, it can be from some tiny 0.1 nanometer, or even below that kind of wavelength, very tiny wavelength, to even kilometer wavelength. It can vary, and depending on their origin and energy, we have divided this electromagnetic wave in different range. So in wavelength, you can see it is 10 to the minus 12 to even 10 to the 4 in centimeters. So how we divided this whole range? The highest energy is called gamma ray, which is very penetrating, huge energy. Then it comes to be X-ray, then ultraviolet, and only this tiny region which is visible, visual, that we see through our eye, because our eye is sensitive to the visible emission. Then beyond that, we have infrared. Many of you have heard about the infrared, this specs, infrared camera, and all this stuff, which is in just beyond the visible range, lower wavelength and higher wavelength and lower energy. And then it goes to microwave. Microwave, we know that microwave that we use for our cooking and all, that works in the microwave range, which is nothing but micrometer range. And then the lowest energy electromagnetic wave that we observe is in the radio range. Okay, so today we'll be talking mostly about observation in the lowest energy range, radio. We are fortunate that our sky, because you know that our sky has an atmosphere, and most of the high energy is actually get absorbed. For looking at our astrophysical bodies in this range, this energy range, actually we need to put our telescope above in the sky. So through satellites, you know that few months back we put this Aditya L1 and all these telescopes. Mostly they are working in high energy, ultraviolet, sometimes IR also is there, but it is very good observed when we go beyond the atmosphere of our Earth, because there is nothing to absorb those energies, and we can uninterruptedly we can observe. That's why the satellites are used in this range. Whereas this in the visible range, there is some kind of absorption, but very less. So in the visible range, we can put our telescope on the Earth surface. It is fine. Beyond that, again, our Earth become this thing. It absorbs. So there is no observable situation on the Earth. to observe that, we have to go again above the Earth's surface, and some kind of this infrared telescopes are put here. We are fortunate that in radio, the sky is totally your transparent. So what we can do, that our radio telescope can be put on the Earth surface itself, and we can very well observe it. Very sensitive observation can be done till few tens of meter. But after that, again, sky becomes this thing opaque. Okay, so this is what, and depending on that, as we discussed, we put our telescopes at different places where absorption is less. Okay, now come to GMRT. If you know that this is one of the world's largest radio telescope owned by our country, actually operated by National Center for Radio Astrophysics. It is situated in Pune, near to Pune, 80 kilometers or 100 kilometers away from Pune. There is one village called Koda. There we have 30 such antennas. Each antenna is 45 meter of diameter, and in the center there are many, and then in 3 arms we put the rest of the telescope. All together we have this center. You can see 12 or 14 dishes are actually there, and these are the arms, which is actually spread over almost 26 kilometers around the this place. So this is till now the most sensitive telescope in radio waves. In the it works in the range of almost 100 megahertz to 1500 megahertz. Okay, in this range, this wide range observation in low frequency, we call it low frequency, that means high wavelength range, is rare. I mean, rare means this is the only one that operates in so large wideband in low energies or low frequencies. And that's why it is very unique, and it has done marvelous discoveries in the past, and currently also doing. We have upgraded it, and upgraded has much more sensitivity than earlier. Okay, so now come to my research, because all these primaries that I have given, basics I have given, will be connecting to the next research. Okay, so in radio waves, skies are very interesting. You can see this is one of the sky survey map. This is at 150, around 150 megahertz. This we have observed radio frequency, and it is in from LOFAR. This is European initiative, though data are available for everyone to work with. So this LOFAR has made a sky survey, and you can see it's a big patch of sky that I'm showing, and each point is actually showing some of the objects. Now, are you, I mean, lost in the sky, right? What is this, and what specific or interesting thing is there? If I ask any one of you, or even the scientists are puzzled that what is there. So you have to make some very systematic approach to understand what is there, or if we see some new object, new physics, anything you can understand, try to understand from this, you need a systematic approach. So what we did is, actually we look for galaxy clusters in this range, and particularly Lobes. It is actually a bigger project that I'm leading, but I'm not going too much onto this. But you think that with some basic features, we have shortlisted these galaxy clusters. Galaxy cluster, as I showed you, the biggest object that we see in the sky is the galaxy cluster, biggest gravitationally bound object that I showed a few slides back. So it shows some of the cluster, depending on some very unique features of them, which I'm not discussing now. But once we shortlist them and then go into the sky, our job becomes easier. right? That we can look into certain region and we know there is already some structure is there. So if you see some emission, we can try to understand that emission, how that emission is taking place, what are the physical processes going on, and all this stuff. So while doing this, actually we are looking for something else. What we found, I will show it in the next slide, but we are not looking for that directly. We are looking something that comes from the galaxy cluster itself. But what we found is, we found something like this. This is one galaxy cluster, Abel 980. This is not the cluster. I will come to that, where how the cluster actually looks, which is can be seen in X-rays. But this is the radio waves that we found from the object. Now, if we try to get what are the components, we see this is one component, this is a big component, and there are two this kind of very point source like component. So what are these? This puzzled us, that what are these? So when we overplotted the galaxy cluster with X-ray, so this is a little bit, I mean, tricky thing that we do in science, in research in astronomy, because we cannot plot two different emissions with color. As you know, one will actually obscure the other. That's what we do, that we keep one in color and other we plot with contours, so that it becomes transparent and both can be plotted on the same graph. So you see, these contours are X-ray contours. That means that I showed you that X-ray emission coming from that electron breaking radiation or so, which is connected to the temperature or thermal energy of the system. Okay, so this looks like this. This is the whole cluster, and inside that, radio emission is taking place like this. Okay, and radio emission, what we told, it is connected to magnetic field and high energy electrons. Fine. Now, going to next slide. We wanted to know that radio emission, from where it is coming. Radio emission is, I mean, it is not connected with the spectral line, so we cannot really locate them, that from where it is coming. As I showed you, in the line of sight, there is a whole range of sky. So whether it is coming very near to us or from very far to us, we cannot understand from the radio emission, but we can understand that from optical emission. Because optical is spectrum, and from spectrum we actually compute something called redshift. Redshift, some of you may heard about that. Redshift is nothing but which says how distant some object is from us. Okay, so with that we pointed out these are the object which is sitting in the cluster, and we tried correlating them with the radio emission. And we saw that in the center of this central object, there is a bright galaxy in optical. So this emission must be connected to that. But these two emissions are not connected to any of the galaxies, which is on the plane of the galaxy cluster. These blacks are not on the plane of the galaxy cluster, only red are. But this is also not connected because this is not at the position where radio emission is peaking. So these are not connected. So these radio emissions are not connected, and this is only connected one. This is what we, when overplotted optical with radio, we got that point. Fine. So now we have to understand, since we got something at the center in the previous slide here and some emission, this is for scientists, it is very easy to understand that this comes from the radio galaxy. But what is radio galaxy? For your information, I have again given some lesson to this, that radio galaxy, initially also I showed, right, that optical and then overplotted radio and then X-ray. That was also a radio galaxy. Here you can see that radio galaxy center is a bright galaxy only. This is optical galaxy, small one. But radio emission in form of jet, they comes out, and then if I okay, I'll come to that point, but let's say it looks like this. We call this kind of narrow laminar flow as jet, where it ends is hotspot, and the whole diffuse emission is low, and this is the galaxy. And there can be various kind of such radio galaxies, these things. So now come to the point how this jet emission takes place. First of all, these galaxies, as I showed you, that center there is a galaxy. So these galaxies, this is the central galaxy. These host black hole. Black hole, many of you have heard about, which consist of huge amount of mass, but in a very small space. Okay, and it does not allow any emission to take place or come out. Fine, but what happens because of that heavy mass? It accretes mass from the around that place and creates a accretion disk. This is the disk that has created. Once this is happening, because it will be rotating, right? It will be trying to pull all the material into the center, but that cannot directly fall. It will rotate like anything, very high speed. Because of that, it gets heats up and many things happens. That's why the radiation is seen. At the same point of time, what will happen is that to conserve, because it will be rotating, to conserve the angular momentum, and the jet, I mean that energy that is going inside, all cannot be just going inside. Something has actually comes out, which comes out in the form of jet. How jet forms, I will come to that point. But because of the high temperature and particle energy, you see that these things emit X-ray and radio waves. That's how we see them. So how jet is formed? So there will be huge magnetic field which will be twisted. This is one of the model. There are various models actually. I should caution you that this is one model I'm explaining. So this magnetic field will get twisted and make a nozzle kind of thing at the end. And because of angular momentum conservation, it has to do it both the side, otherwise it will get disbalanced. So both the side there will be a nozzle formed due to this magnetic field twist, and then from that nozzle the particle that is accelerated will be thrown out with a huge speed. So thrown out means it will be like a jet. You have seen the jet plane. It emits some white kind of cloud in the sky. We see initially there is a very narrow laminar flow and suddenly gets spread out. Why it happens? Because when the velocity is huge, it will cross all the space, because it will have so much thrust that no one can stop it. But slowly it will lose energy, and at some point of time it will get diffused out, right? So that's how the lobes are formed. So initially channel like jet, and then the lobes will be formed, as we saw in the last image. They can be in various form, various angle, and depending on that, in radio we see different kind of galaxies. Now what happens? This emission takes place, and sometimes after emitting for some time, it stops. Why it stops? This is still under research. We don't know, but it stops. Again, it starts emitting. If that can be some explanation is that that two black hole merges sometime, they get flips, various kind of things happens, and then they stop emitting and again start emitting. So these are called the recurring radio jets. These are connected to the discovery that we have made. That's why I'm explaining. So if you now try to think about what is the emission that is taking place and how they evolve in time, you will see that most of the energy that is coming from synchrotron is in some frequency range. So if you plot it in frequency, there's low frequency, medium frequency, and high frequency, because everything we observe electromagnetic wave, and electromagnetic wave have a characteristic frequency. So let's say we are observing in a large frequency range. At this moment I'm stick to radio only. So radio can vary from microwave to kilometer wave. So let's say we are looking at that. So this way it is microwave, and this way it is meter or kilometer wave. So what happens that because this side it is low energy, when jet emits, because of some that particles are around, it will get obstructed and that part the emission will be absorbed. It is called self-absorption, because the electrons that is emitting, the same cloud is actually acting as absorber. But on the higher energy side, what will happen, as it goes higher and higher energy, there will be radiation losses, kind of inverse Compton we call it. So that radiation losses, what will do? This is a power law, that means it's a linear in log scale. And because of this interaction or radiation losses, this slope will be becoming steeper. Okay, that means now you see that here energy is very high, but here because of the loss, energy will be low. That means if you put your telescope to observe this, while you will be able to observe this region will become fainter. And up to the time that jet emission is active, these losses are actually compensated by the new jet emissions. But when it stop emitting, what happens? These radiation losses will start dominating, and then the spectrum get curved, and you see that your object will vanish from the telescope because it is started emitting low energies. Okay, so this is what is happening. We cannot see the same thing in the same galaxy because it's a huge time that it takes to do all this stuff. So we took similar kind of two galaxies and tried looking at it. So if you see that this is one galaxy which can be very which has very bright lobes. Okay, we can very easily detect them. Another similar type of galaxies, if you see here the galaxy is, and the jet and lobe has got diminished, very much diminished, because it has lost energy and it is in the high energy range that we are observing this galaxy, and we see this has been almost gone. So that means what happens, that some galaxy will be bright, having bright lobes, and some galaxy will have lesser bright lobes because of these energy losses. So in the sky we will see many of them, and this is directly connected to the age also, because I told that as it goes older, the emission will be less. Okay, so that thing actually come out in the spectrum. So this is some galaxy cluster we see, and if we see the spectrum, if you see in that, this becomes steeper, as I showed you in the earlier this thing, that this is what in low energy, and high energy it goes to very steep. So if you observe in two frequencies and plot them and try to get this nu to the power, it will be very, very steep in case of older one. That means from this information we can actually get what is the age of the object. So that is what we have done for our object also. So we have observed in various frequencies and then tried plotting the your slope. Then as we go in some of the region, we saw that is very steep, becoming very steep. You can see here. So this is minus 0.5, minus 1, minus 1.5, minus 2, minus 2.5, and minus 3. That is very steep spectrum. You can see these regions are very steep spectrum, while the active regions are flatter. Okay, so now as I told you, this will give us the age calculation. You see, this is the age of the electron population, and what we see that this is something beyond 150 or 160 million years of age, and some region goes beyond 200. We saw the maximum maximum age of this region found to be 260 million years. Now, thing is that this kind of aged electron population or the lobe could not be detected earlier. So we are the first one to detect such an old electron population, or which we call the radio lobe, in whatever so many years of radio astronomical history. What significance it has? That means now we can study the jet evolution for much longer time. Longer time means not in the human time scale. I am talking about the evolution time of the jet. But there were some issues that earlier no one has detected anything beyond 100 million years. So how we detect some population which is 260 million year old? That was a puzzle, huge puzzle, because no one even expect to have that. Then we found that this galaxy is situated within a cluster, as we started with, right? It is within a cluster, and cluster may have some certain condition. Certain condition means cluster actually have diffuse emission which has huge temperature. So in a temperature, if there is a huge temperature around, what happens? This radio emission cloud, which is actually called non-thermal cloud, get trapped within those cluster medium. Once it gets trapped, what happens? Inside it gets pressurized to keep the material alive, means hot. Hot means here it is not really hot, it will be energized. If that keeps energized, then at a very old age also it will try to emit something, and that is what exactly happening here. So I'm not going into these details. We detected some shocks around to prove that there is some confinement happening. And this kind of situation can only happen within a galaxy cluster and specific kind of galaxy cluster. And that's how this whole material got trapped, and it has still kept emitting after becoming so old. So that was a huge discovery. And if you see, we have actually seen that how the temperature is. This is a temperature map. This is in Kelvin scale. And we saw that both this radio emission actually trapped within this high temperate emission. We could not map it full, but whatever portion we could map with the data that we had is enough to prove that it has been trapped within hot gas. Okay, so this was the discovery and the uniqueness of this discovery, and that is the reason that this has been actually press released by GMRT Mother Institute, that is NCRA TIFR, and this got huge attention in the media also, in foreign media as well. But that is not the thing that we discuss, because media can take anything, but most encouraging thing is that with using our own telescope, we have discovered something which is very unique and has implications in physics of radio galaxies, that help understanding the physics of radio galaxies much better. Okay, so this ends the talk, but not fully. I will just complete it in a few minutes. That what we have done is that discovery of a remnant radio lobes with a record age of 260 million years. This has been published in one of the top astrophysics journal in 2022. But question is that, is it the only one? This is maybe unique one, right? We saw that this is a unique one, but is it a only one? Let's go into the sky, real sky. So this is at high frequency NBSS. Quite few years back, this some sky patch has been observed. You can see that there are bright sources somewhere scattered around the sky. And we know that if the spectrum is very steep, at low frequency, we'll observe many of them. right? And that is what the recent survey of from LOFAR has done. See, almost the same region of the sky, and you see so many objects. So if you see these and these, so scientists gone mad that so many objects are there, which may have very steep spectrum, and we cannot guarantee that out of them many may be having the same situation as we have discovered. So that is the case, that what discovery you have done is very unique, but that is not the end. It is the starting point. We may have many such things in the coming year. We may discover many of such radio galaxies, and that will really help us in exploring the sky and understanding the physics of the formation of these galaxies much better. So thank you, and you may ask any question as you want.
Thank you, sir. Any questions?
Dr. Paul, it was really good talk. For this particular analysis, only GMRT data was used, or any other foreign radio data also was being used?
Okay, so we have mainly used GMRT data, but also LOFAR data is there. I mean, in the next paper, we used LOFAR data, which I did not talk about, but we have used LOFAR data as well. And the age one that I have shown, that one has been calculated using LOFAR and GMRT both.
Thank you. One subsequent question is, I understand radio astronomy is oldest astronomy, but in the current trend and with your new, what you call invention, what is the scope for students to join radio astronomy?
Okay, so one thing I should say that it is not oldest. Oldest must be optical, because that is how the instruments has been developed. But yeah, radio astronomy is also not very new one. From 1960s and onwards, it has started. So thing is that this at this juncture, at this point of time, it is very important for student to actually get attracted to radio astronomy. Why I am saying that, till last decade we have a few sensitive telescopes only. Okay, like GMRT and VLA and ATCA, that is in Australia. But in the last 5-7 years, we got a few more very sensitive telescopes. One is our own UGMRT, upgraded GMRT, and the LOFAR already we have seen, and Meerkat, and some precursors of the square kilometer array. It does not end there, because now we are actually we are also a part of this effort, which is called square kilometer array, and which is a global effort actually. It will be constructed in Australia and South Africa because of the I mean, very good position, quite position available there. But it is an effort by 10 to 15 countries all over the world. Everyone is putting money, and the scientists are involved. We are also involved in this from our group here, MCNS. And that is going to change the sky of the radio astronomy hugely, because that has a sensitivity 10 to 100 times more, in depending on various frequencies, more than what currently we have. So you can understand that what kind of revolution is going to happen in radio astronomy. And I assure you that in the next 10 years or 15 years, actually radio astronomy will dominate the science. It's a huge opportunity at this moment for the students to come into radio astronomy.
Thank you. I think I understand even Gauribidnur radio facility also is upgraded. All over India, many
Yes.
radio facilities are being upgraded. It
Yeah,
may be
yeah,
a good
yeah.
opportunity for students to pursue in this direction. Thank you
Exactly.
so much for your excellent talk.
Thank you.
Any more questions? Venkat?
Thank you, sir, for the awesome talk. Do you have any questions as well?
I'm not able to hear you. Can you please loudly speak?
Thank you, sir, for the great talk, but I don't have any questions as of now.
Oh, there is no questions. Okay. Is there any in the box, chat box or so? Can you please check?
No, sir. I think.
Nothing. Okay, fine. Yeah. Okay.
Okay.
Thank you then.
Sir,
No, one
thank you.
second.
Huh.
No, 1 second. Let Dr. Paul explain Maha efforts in astronomy so that it will be on record. Students can refer what are all the student opportunities available in Maha. Maybe very briefly.
Okay, so that is a good thing because in Mahe, this I'm in the Manipal Center for Natural Sciences. So in this center, actually, most of the faculty members are involved in working in astronomy or astrophysics in general. So most of the faculty members are there are also nuclear physics person and chemistry and biology persons, but the bigger group is astrophysics. And we have together with our director, we are like 10 astronomers working here. And best thing is that everyone works in different field, but we have some common interest as well. So different field means different waveband. So starting from gamma rays to X-rays to optical, infrared, UV and radio. So all kind of scientists are there. As well as this is the observational science. Not only observation, we also do computational. Like myself itself, I myself do computational astrophysics, and there are theoretical astrophysicists as well working on cosmology. Some working in the gravity, and there are people even in the high energy astrophysics part. Okay, so these are the various things that is going on here, and all of we are actually connected to very research at the forefront that is happening, and connected to various facilities as well. There is also instrumentation, as you know that in Aditya L1, we have a scientist here who is involved in Aditya L1 in the instrumentation as well as the science part. So there is huge opportunity that we have in Manipal Center for Natural Sciences, and we have two different programs. One is integrated MSc PhD. So what it is that people from after BSc can come and join here as the MSc student. There will be 2 years MSc, but MSc by research. So 1 year will be coursework, and another one fully on research. Research means in the advanced field of research. It's not just reproducing something. You will publish papers out of that. That kind of research is going on in will be done in the MSc second year, and those students can also continue for their PhD. While MSc is self-funded, the PhD part we fund them. We provide them fellowship and all. That is for 3.5 years fellowship. Fully fellowship will be given to those students. This is one
The
scheme.
entrance exams are required, sir.
Yes. There is entrance exam, but unfortunately, this year's entrance exam is over just now. But student for the next year they can try for integrated MSc PhD program. For the PhD program, we directly also take from for PhD. So that is announced every year twice during one is in December, I think November, December. Another is in June, July or something. Okay, just keep looking at the website. That will come out at that time. So there also we have the fellowship, full fellowship for the student for 3.5 years, and later on some other funding can be arranged depending on how much time it takes. But we expect that student will finish it by 4 years of time at most, the PhD.
Sharing your knowledge. Thank you, one and all, for joining with us. Thank you, Paul, sir.
Thank you.